So as we begin looking at probability and statistics, I want to first of all not take anything for granted. I don't want to assume that you know about certain things, okay? Especially with the variety of backgrounds that we have here. So I want to just take a quick look at some of the items that are commonly referenced in probability problems. I know not all of you are necessarily used to American money, okay, but a lot of times they'll talk about coins, all right, heads and tails, okay. If you see the picture in American money, if you see a picture of somebody's face like that, that's the heads, and if you see something else, that's known as tails, okay. So pretty simple, and probably a lot of you have used that before, but I know some people may not be as familiar with that. Another thing is rolling dice, okay? Rolling dice, unless they say otherwise, they're talking about a die that has 6 sides. It's numbered from 1 to 6, okay? So we roll it and we can get, anything. And all of those numbers are equally likely, okay? Every time you have a 1 in 6 chance of getting any one of those numbers, all right? So that's pretty simple as well. The last one, though, I'll take a couple minutes to explain, is the standard deck of cards. We use this one a lot because there's a lot of different varieties of things that we can consider when we're looking at a standard deck of cards, okay? How many of you are familiar with what a normal deck of cards is? Okay, so a lot of you are, some of you are not, and that's okay. If you're not, getting the notes off of the website and just printing out this one page as a reference sheet might be helpful for you. Okay, but you have a standard deck of cards. There's a couple of things that you ought to be familiar with about it. Okay, for one thing, there's 52 cards total. Right. Put it away. There's 52 cards total. All the cards are either red or black, and there's an even number of them, so there's 26 red and 26 black. There are 4 suits, okay? The 4 suits, we've got diamonds. The suits are the different shapes that are on them. So diamonds, we have clubs. There's these things that kind of look like a clover leaf. We have the spades. They look like the spade shovel that you might use in gardening. And we also have hearts, okay? So we have our 4 suits. Each of those, because there's 52 cards in the deck, each of those has 13 cards, okay? The hearts and diamonds are red, the spades and clubs are black. And in each suit, we have these cards. The 13 cards start with ace, that's like a 1, okay? Ace through 10 are the first 10, and then the jack, queen, and king are like the 11, 12, and 13. Okay? The jack, queen, and king are known as the face cards because they have people's faces on them. Okay? So here are the aces. Those are the ones. The face cards have the different faces on them. Okay? So, and obviously the king has the K, the queen, Q for queen, and J for jack. All right? So, any questions about a standard deck of cards? Particularly. Okay, we'll be using it a decent amount, so those are some facts that you're going to want to, review if you're not already familiar with them. It kind of just depends on your family. If you grew up playing cards, you probably are real familiar. If you didn't, then it may just be something you just have to get used to dealing with. Okay. I will say, if it comes down to we're on a quiz or a test or something, and you just can't remember how many cards are in each suit or something like that. That's the kind of, I'm not testing you on, how well you know a deck of cards. If it's a simple question like that, I don't mind telling you, okay, because that has nothing to do with the math. So, let's now talk about counting principles, okay? One of the things we're going to be doing with these is finding probabilities, and to find the probability of something happening, we have to consider how many different ways it's possible for that thing to happen. And that's why we have to count them. There's an entire branch of mathematics called combinatorics that basically all they're doing is counting stuff. All right? We're counting stuff. How many different ways could we do this? How many different ways could we do that? But when you're approaching a problem, there are really three questions you kind of need to consider as you are trying to count things. All right? First of all, does the order I'm selecting things in matter? Okay? Does the order matter? In other words, one of the things that you can kind of ask yourself is, when I pick things out, are there going to be distinct positions that they're placed in, or am I getting a group? Okay? Am I getting a group, or are they going to get put into positions? And here, really the key is the difference between, are you doing a permutation, an arrangement in order, or a combination, where we are just collecting them into a group. Okay? So, again, with order, think, positions. If we're trying to pick, the president, vice president, and secretary for the class, then the order we pick those people matters, because if we're going to make the first one be the president and the second one be vice president and third be the secretary, then the order we pick those people in matters. Okay? If we're just coming up with a committee, a committee is one example, or a board, where there really aren't positions, we're just dealing with a bunch of equals, then in that case we would use a combination, because the order doesn't matter. Okay? They're all on the same team. The second question we need to consider here is, are the items being replaced each time one is chosen? Okay? So for example, if I were picking some of you to come up and do a problem on the board, all right? If I just randomly picked anybody the first time, and then after you sat down, I went ahead and just randomly picked someone again, what could happen?
Same person.
I could pick the same person again, all right? I replaced that person into the pot, you could say, or into the pool of possibilities, and I could pick them a second time. However, and by the way, that is the kind of thing that would make events independent, all right? Because it doesn't matter who I picked the first time, everyone has the same chance of getting picked the second time. All right? As opposed to, we have 20 people in here. If I pick, Callan the first time, everybody only had a 5% chance of getting picked, because there was 1 out of 20. Well, if I don't put Callan back in the group that I'm going to pick from, now I'm only picking out of 19 of you. So you actually have a greater chance of getting picked the second time than you did the first time. There, I did not replace it. Those would be that would not be independent events, the first pick and the second pick. However, when I do put that person back in the group, or I replace it, then the first one has no impact on the second one. Those are independent events, and we're going to treat that a little bit differently when we're doing work with them. Okay. Getting back to our standard deck of cards. Okay. Let's say I pick a card out and I get the Ace of Hearts. Okay. And I pick that out. If I'm going to pick a second card, and I don't put that back, then I have an equal possibility of getting, or I have a greater possibility of getting all the cards the second time. Okay? However, if I put that card back in the deck, I could pick the Ace of Hearts again. Okay? So that would be independent, because I had the same probability of getting that same card the second time, or all of the cards the second time. Okay? So that's independent. Another thing we have to consider is when we're talking about two different events or two different outcomes, is can they occur simultaneously? And this one is a little bit challenging to make sure we understand. But can they occur simultaneously? For example, let's say I'm considering the color of the card and the suit of the card. Okay? Is it possible to pick out a red heart? Well, yeah, all the hearts are red. Okay? So, picking a red card and picking a heart are not mutually exclusive events. However, I can't pick out a black heart. Alright? Those would be mutually exclusive because they cannot happen simultaneously. They can't happen in the same drawing of the card. Alright? Some other examples using the deck of cards. I'm going to use it a lot today, especially just so we're getting used to working with these. Okay? You cannot pick one card that is, well, we already said a heart and black. Okay? You can't pick a card that is, let's say, a 6 and a face card. Alright? It's impossible. There is no 6 that's also a face card. Alright? Obviously, you can't pick out a card that is both a red and a black. Okay? They're one or the other. Alright? So all of those things would be mutually exclusive events. Alright? Sometimes it's a little more obvious. Sometimes it's not as obvious. So you really have to pay attention when you're counting things up, that you are careful to consider these three questions. Alright? Does the order matter? Are they independent events? And can different outcomes occur simultaneously? Are they mutually exclusive events? Okay? It is possible for things to be both independent and mutually exclusive. Okay? Now, let's talk about actually getting into counting. How do we count up how many different ways we could do something? The fundamental counting principle, I'll show you what's in your book and then we'll explain, okay? So let's say we have two events, E1 and E2, all right? E1 and E2. And E1 can occur in M1 different ways, okay? E2 can occur in M2 different ways, all right? So the number of ways that the two different events can occur is M1 times M2, okay? So we're counting up how many different ways two different things can occur. This can take a lot of different, this can be used in a lot of different contexts, okay? Let's say that you're taking a trip and you're going to drive from here down to Fort Lauderdale and then you're going to go from Fort Lauderdale down to Miami, okay? Well, how many different paths could you take to get from here to Fort Lauderdale? Okay, there's a lot, okay? Well, let's say that, you get on Google Maps and it proposes 4 different paths you could take, okay? So, to go from Coconut Creek to Fort Lauderdale, let's say there are 4 paths. And then from Fort Lauderdale to get down to Miami, those are a little bit closer together. So let's say that, Google only proposes 3 possible routes. Okay, now obviously with all the different streets, there's millions of different ways you could get there. We'll just go with these ones. All right, so how many different ways could we get from here to Miami? Well, 4 different ways to get to Fort Lauderdale, 3 different ways to get the rest of the way to Miami. So we would have a total of 12 different possibilities. 4 times 3. There are 12 different routes that we could take. Okay? Because each of these 4, for the first leg of our trip, has 3 possible second legs of the trip. Okay? So 4 times 3 would be 12. You could do any of a number of things, okay? One time with a class we did Baskin Robbins. How many flavors do they have? 31 flavors. Okay? So if we have, I'll put this down here. Let's say we've got 31 flavors. And let's say you could get it in a regular cone or a sugar cone or a chocolate dipped sugar cone or a cup. So there's 4 different ways that you could get it. And how many toppings are there? Like, I don't know, what, maybe 20? Okay. So, let's say you were going to make some ice cream with 1 flavor and 1 topping, okay, to keep it simple. That's how many different options you have, okay? So 31 times 4 times 20. That would tell you how many different possible options you could order, okay? And let's see, what would that be? 124 times 2 would be 2480. 2,480 different possible orders that you could put in. And that's if you just get 1 kind of ice cream and 1 topping. So you guys can see how our numbers can actually get really big really fast. And we're going to have some big numbers in this unit. All right, you guys can handle it. All right, so let's consider another case here. Suppose we pick 2 cards from a deck, replacing the first one before we select the second one. Okay, so we're dealing with independent events, the 2 different choices. How many ways could you pick a diamond the first time and a face card the second time? Okay, well, how many different ways could we pick a diamond?
13.
How many?
13.
13. There's 13 diamonds in the deck. Okay, so there they are. There's our 13 diamonds in the deck. And how many different face cards are there?
12.
What?
12.
12. Yeah, there's 3 in each suit, and there's 4 suits. So there's 12. There's our 12 face cards. All right. Let's get that blue. Now, in this case, drawing the face card would be our event 2, and drawing a diamond would be our event 1 to kind of go along with what we were given up here. Okay? So the number of ways that event 1 can happen would be 13. The number of ways that event 2 can happen would be 12. And then you would just multiply those together. So how many different ways could we get?
156.
Yeah, 156. All right. So we have 156 different ways we could get that combination of cards. Yes? Any questions so far? Okay. So, next what we're going to look at is starting to arrange things in order. Okay? We mentioned this term already, the permutations. Okay? Permutations. You see some notation that's similar here. Okay? NPR, okay, it's not National Public Radio, it's permutations. How many ways can we arrange our items out of a total of n items in a distinct order? Okay? Now, we're going to start first of all looking at examples where we're arranging all of them. So this would technically be NPN. All right? We're going to arrange all of the items. And this actually makes sense logically if we just think our way through it. Let's say that we have the 6 letters A, B, C, D, E, and F. Okay? Now, one thing that can be helpful when you're doing a problem like this is to kind of draw the different positions. So we have 1, 2, 3, 4, 5, 6 different letters that we got to fill in. Okay? Now, we're arranging these letters, so once we use one, we can't use it in another spot, right? So, how many letters do we have to choose from for the first number?
6.
We have 6. Okay? Now that we've used one up, how many do we have to choose for the second? 5.
5.
And the third one?
4.
And
3.
then there's only one letter left, right? Okay. Now, what you need to kind of consider here is that each of these things is like an event. If we're thinking in terms of the fundamental counting principle. There's event 1, event 2, event 3. We're placing a number, or I should say in this case, we're placing a letter. Okay? Event, whoa, went the wrong way. 4, 5, and 6. Okay? So we have 6 events. And we just figured out what the number of ways each event can occur is. So what do we do with all those numbers?
Multiply.
We multiply them. Okay? We're going to multiply these together. Now, does that look familiar? How else could we write this?
Similar.
Factorial?
Yeah, this is 6 factorial. Okay, which is 720, but okay, this is 6 factorial. So you can see we're going to be dealing with factorials again here. Now, this is what we can see here. The number of permutations, if we are arranging all the elements, okay? And again, what we're basically doing here is n permutation n, okay, is just n factorial. All right, so don't overcomplicate these ones. If all 20 of you were running in a race and we wanted to see what order you could finish in, how many different ways could that happen? 20 factorial, okay? 20 factorial. Now, where it gets a little more challenging is when we don't care about the last however many, okay? Are there any questions on this before we move on, though? All right, good. So, let's say that we're only looking at a few of the total. So here we have 8 horses running in a race. How many different ways can these horses come in first, second, and third? Now there's a couple of things here. Remember we said the first question you got to ask yourself is, does order matter? Notice it doesn't say how many different ways can they come in the top 3. If they said that, that would just be a group, right? But here it said come in first, second, and third. So the permutation is necessary here. The order matters. But in this case, we only have 3. So first place, second place, and third place. Okay? So, how many different horses could finish first? 8. Alright? How many horses could finish second? 7. Why not 8?
Because one's gonna finish first.
Yeah, and finishing first and finishing second would be considered
Impossible.
impossible to do at the same time, right?
Yeah.
So it would be,
Usually that's exclusive.
yeah, we would consider that mutually exclusive. Finishing first and finishing second, the same horse can't do both. So that'd be mutually exclusive. Third place, how many horses could finish third? 6. Alright, so 8 times 7 times 6, which would be 42. Let's see, that'd be 42, 84, 168, 320, 336. Is that right? Okay. So there's 336 different ways if you were trying to guess out of the 8. You know, you just picked 3 horses at random. You have a 1 in 336 chance of actually getting it right. Okay, so not really good. But there is an easier way. Okay, and the easier way is to use the permutation. Okay, here you see a formula that's very similar to the combination formula that we had before. NPR equals n factorial over n minus r factorial. Okay, how is this different from the combination formula?
There was something after the n minus r. It was like minus r factorial or minus n.
It wasn't minus, it was just
Times.
times the r factorial. Good, okay. Yeah, the combination had this. Now, what that did was eliminate all the permutations of the groups that had the same members. Alright? Well, now we want all the different arrangements or permutations of those groups with the same members. Alright, it's not enough to know that these three finished in the top three. Now, how many ways could those three be arranged in the top three? That adds more possibilities here. Okay? So, but you see the rest of it's the same. Okay? Now the n factorial, that's if we were arranging all of them. The n minus r factorial, that eliminates all the ones we don't care about. Okay? So, in this case, we're going to do 8 permutation 3. So we have 8 factorial. That's how all 8 horses would finish. And then that's going to be over 8 minus 3 factorial. We're dividing by this 5 factorial because we don't care about the last 5 horses. Okay? All we care about is the top 3. So we're dividing by the 5 factorial. That gets rid of those. So now, remember how we can reduce fractions that have factorials. And again, you have 876, which equals 336. Okay? Make sense? All right. It's not too hard in theory. Once you get into the word problems, it can be a challenge. All right? So really take time to practice. Now, because of the holiday, the independent practice, and because of our test, there's independent practice listed for today and tomorrow, okay? Those we will not take a look at until Friday, okay? So those are not, don't feel like you have to go home and do them all tonight. But we will look at all those on Friday and answer questions, okay? All right. I think we are, yeah, we're done. All right, have a great day, guys.